All right, so today we are talking about the derivative and graphing, okay? So basically you guys are going to be able to use the first and second derivative to graph functions, to determine extrema, and as well as concatenate. So by the end of the lesson, you'll be able to see how the first derivative and the second derivative connect to the graph of the original function, okay? So you guys are going to be basically graphing functions, but more in the sense of like not so much quadratics, but more like cubics and quartics, rational functions, and things like that, using derivatives. Okay, so make sure you guys get down the goal, and once I file these away, we'll get started. So basically, I'm going to kind of go through all the notes first, and then we'll go through the examples because basically, everything ties into each other. So I'm not going to split it up and say, okay, here's this one particular topic. Let's do an example. No, we're just going to go through it all, and then we'll just hit the examples after that. Okay. So we have three graphs here. And I've asked the question, where are these functions increasing and decreasing, okay? If we look at the very first one, okay, yes, this is a quadratic, and so the function is increasing from where to where, would you say? From what? Negative infinity to what? To negative 3. Very good. Okay, increasing basically means the graph is going up as you're going from left to right. It's just like a book. We read graphs from left to right. So it's going up from negative infinity to negative 3. And so what's happening from negative 3 on? It is decreasing, okay? So negative 3 to positive infinity. We use the x values, not the y values, to determine where a function is increasing and decreasing, aka going up or going down, okay? Let's look at this next one. This is 2 to the x, an exponential function. This is what? Increasing or decreasing? From where to where? Negative infinity to what? Into positive infinity. Yes, okay. Exponential functions, especially like your most basic ones, they are exponential growth, so they're increasing, they're growing on the entire interval. And then what about for this one? What's happening? It is increasing in two different places, from negative infinity to negative 1 and from 1 to infinity. So what's happening in between negative 1 and 1? It is decreasing, okay? Simple enough, yes? Okay. Now one thing you need to be aware of is, so, back to my original thought until we get where the graphs is. All right, so basically, increasing where the graph's going up, decreasing where the graph's going down. Something that you should notice is that there's a point on any part of your graph, the tangent line, the slope of the tangent line basically will tell you whether or not it's increasing or decreasing. If you look at this particular point, the tangent has a, what kind of slope? It's a positive. Take a look here, okay? If you draw a tangent line on this respective point, again, the slope is positive. If you draw a point here, the tangent line has a what? It's a negative slope, so basically it's decreasing at that particular point. So you can actually use the tangent lines, the slope of the tangent lines, to determine whether or not a graph is increasing or decreasing, okay? It's positive, it's increasing, negative is decreasing. So, using that whole concept, tangents, slopes of tangent lines relates to the derivative. If the first derivative is greater than 0, then the function is increasing on a particular interval. But if the derivative is negative on a particular interval, then the function, the original function, is decreasing, okay? So these two features basically tell you what's happening on the original function, okay? And vice versa. If you look at the original function, you see it's increasing, then you know the derivative is positive on that particular interval. And if the original function is decreasing, then you know the derivative is negative, okay? Questions up here? So, a function has a relative, or aka a local maximum changes from increasing to decreasing, okay? And likewise, if a function has a relative local minimum, it's changing from decreasing to increasing. Okay, maxes and mins are known as relative extrema of a particular function. So if the question asks you to find the extrema, then basically it's asking you to figure out where there's a max or where there's a min. Okay? So if we're going from increasing to decreasing, decreasing to increasing, we'll have a max or a min, respectively. Okay? If you take a look at those examples from before, as you can see where the graph was going from increasing to decreasing, isn't this a maximum point? Yes, it is. And here, since it's increasing the entire time, is there any extrema? No. Okay, as we see, it's increasing and then it's decreasing, so that means that there's a max, and as it's decreasing and then increasing, it's a min. Okay, so as it changes, you basically can kind of know, based off of the derivative, whether you're going to have a max or a min on your original function. Okay, you got to look at the slopes of the tangent lines. Okay? Again, here's some more examples, okay? Increasing, decreasing. You have a max. Decreasing, increasing. Or less than 0, greater than 0. Negative, positive. You have a minimum. If you look here, you have a tangent lines are positive. Right here, what's the slope of the tangent line? 0, okay? But then it's going to increase again. Since it's increasing 0 and then increasing again, there is no max or min. The only time you're going to have a max or min is if you change signs. And vice versa. You're decreasing, 0, decreasing, there's still no extrema. You have to change signs in order for there to be an extrema. Everybody understand that? So then you have what's known as the first derivative test that basically sums this all up. The first derivative test is used to locate extrema. If f is defined at a critical number c, okay, a critical number c, then if the first derivative changes from positive to negative at c, then f has a relative maximum point at c f of c. And vice versa, if the first derivative changes from positive to negative at x equals c, then f has a relative minimum at c f of c. Okay? And so basically you're going to use the first derivative to determine your extrema. Okay? So to use the first derivative test, clearly you need to know what the first derivative is. A critical number, also known as a stationary point, is basically the point where the derivative equals 0. Okay? You remember when we were doing the motion diagrams, motion line, right? Motion of a line? And you took the first derivative and you set it equal to 0, you're trying to figure out where the object's moving left and right, up and down, and you made a number line. We're still going to do the exact same thing here. The first derivative test is basically using the number line. When you find where the first derivative equals 0, let's just say it's at 2. Let's just say it's at 2. And you do your test points, right? If it's positive here and it's negative here, then that's letting you know that there is a maximum at 2. So C would be 2, and then how would you find the y coordinate? Plug 2 into the original function, okay? That's how you would figure out exactly where the maximum is on the graph of the original. And vice versa. You would set the derivative equal to 0, solve that, and then those will be the points where potentially there could be a maximum or a minimum. You do your number line, pick your test points, and see where it changes from negative to positive to determine where there's a minimum. Okay? Now, not every graph is going to have a max or a min. That's why you do the first derivative test to determine whether or not the signs are changing. Okay? So, first derivative test, find the derivative, set it equal to 0, number line. Questions about what the first derivative does? It locates extrema, tells you where you're increasing and decreasing. Whereas the second derivative talks about concavity. If the second derivative is greater than 0, then you know on the original function it is concave up on an interval, A to B. If the second derivative is less than 0, then the original function is concave down on that interval. So concave up, okay, concave down. So basically the graph is in the downward shape or the graph's in the upward shape, okay? Now the points on the graph where there is concavity are called inflection points. It is a point on the graph of the original function where it basically changes from concave up to concave down. That's what an inflection point is. And you'll know if you'll have an inflection point if two things are true. If the second derivative equals 0 and the second derivative changes signs around that number where the second derivative equals 0. Okay? So again, you have yet another number line here. And we've been kind of already dealing with number lines and things when we're talking about motion. Okay? The second derivative, when we're talking about like motion and things like that, was talking about acceleration, right? It told us, you know, we compared the signs between velocity and acceleration, the first derivative and the second derivative. In the sense of graphing functions, okay? The second derivative will tell us when the graph looks like this versus when it looks like this, okay? And that point where it changes from being concave down to concave up is called your inflection point. Now, just like before, not every graph is going to have an inflection point. To determine whether or not you have an inflection point where it changes from concave up and concave down, you make yet another number line. And you pick your test points, okay? If 3 is the point where the second derivative did indeed equal 0, and it changes signs, then you know that there's an inflection point at 3, okay? And of course, it is a point, so you take 3, plug it into the original to get the actual coordinate where it changes, but then you'll know it's concave up and concave down at that respective, on either side of that respective inflection point. So here's an example, okay? Let's say that's 3, 7 or something, okay? You would be able to determine by using the second derivative of the original function that there's an inflection point at 3. Because when you set the second derivative equals 0 and solve it, you'll get x equals 3, do your test points, and it would go from positive to negative. Or sorry, negative to positive. It's concave down to concave up. Okay? So we're going to use derivatives to graph a few functions. Now, using your knowledge about quadratics, about rational functions, about what a cubic function could look like, et cetera, can be helpful, okay? Because if you already know what a quadratic looks like, and you do the derivative, you do everything, and what you get does not look like a quadratic, then you know something is wrong, okay? All quadratics look like this, or like this, okay? Based on the leading coefficient will tell you if it's up or down. This right here on this screen, this is an example of a what? It's an example of a cubic, more specifically a cubic that is negative, okay? So you kind of have, if you use what you kind of already know, you should know what the graph should look like as you're doing the different things to determine exactly where there's a max and where there's a min, or where there's an inflection point, et cetera, okay? Same thing with rational functions. You remember with the rational functions little section that we did? Rational functions have what other features in the graph? Asymptotes, okay? So you know that you're going to be dealing with vertical asymptotes as well as horizontal, and using your knowledge of those things can also help you with graphing, okay? And last but not least, how do you find an x-intercept? Said y is equal to 0. How do you find a y-intercept? Plug in 0 for x. So you're using all the things that we kind of already talked about can help you when it comes to graphing these functions. So we're going to use the derivative of f to find the intervals in which a function is increasing or decreasing. I'm basically breaking this down into pieces and showing you how each of the parts are used to determine this. So increasing or decreasing means we need the derivative. First one. What is the derivative of 2x to the third minus 3x squared minus 12x? Okay? And in order to figure out where it's increasing or decreasing, we need to do our number line. Now, in order to do our number line, we need to figure out our critical values, our stationary points, which means we need to take the first derivative and not plug in 0, but put it equal to 0. And since this is a non-calculator section, clearly the quadratic that you're going to be dealing with, or whatever function you're going to be dealing with, it should be factorable, easy to solve, okay? When you factor this, First thing you look for is there a GCF? What is it? So when I take out a 6, I have x squared minus x minus 2. What two numbers multiply to give you a -2, add to give you a -1. A little louder. -2, +1. So we need to solve this, and x equals 2, and x equals -1. Remember, we're not concerned about that outside 1 unless it was like a 6x. Then we'll also have 0 as well. So those right there are our stationary points. We need to determine if those are actual maximums or they're actual minimums. Okay? So we need to make our number line. Put -1, +2. Remember, negatives come before positives. And now we need to do some test points. We need to test 3 different regions. Less than the -1, what's the number we can test? -2. In between -1 and 2? 0. Greater than 2? 3. Now these are just 3 test points that we chose. You could have picked -5, +1, and +10. Either one would still determine whether or not this is increasing or decreasing. So you take these 3 purple test points and you plug them into what? What tells you whether or not a function is increasing or decreasing? So you got to plug these test points into the derivative, okay? You got to plug those test points into the derivative. And we're not so much concerned about what the number is, more about whether it is positive or negative. So we're going to plug -2, 0, and 3 into the derivative, and we're going to determine where it's positive and negative. So you guys go ahead and do that. What was it at -2? Positive. It was positive at 0. And at 3? Positive. Okay? So it's asking where are the intervals where it's increasing and decreasing. Based off of our number line, we can see that it's increasing from what? To what? -1. And where else? 2 to infinity. Where is it decreasing? -1 to 2. All right. So we have to use the first derivative test to determine our relative extrema for that we just did. Okay. So the first derivative test is the part of doing the number line. We determined that it was stationary at -2 and 1. And that it went positive, negative, and then back to positive, right? So, if it goes from positive to negative, that means what's happening at -1? It's like what at -1? It's a maximum. It's a relative maximum at -1. Now, how do we find the actual coordinate of the maximum? Plug -1 into the original function. That's how you get the y coordinate. Plug -1 back into the original function, guys. Do that real quick. What do you get when you plug -1 in? It is 7. Okay, so that means that on the graph of the original function, there's a maximum at -1, 7. Okay? So let's look at the next one. We go from negative to positive, decreasing to increasing, which means there's a what at 2? There's a relative min at 2. We find the y coordinate by plugging 2 into the original. So let's plug in 2. What's f of 2? -20. So at 2, -20, there's a relative min. Okay? And so, you see what I did here by drawing these little things here? If you forget which one is the max or min, just kind of do it yourself. You need to be increasing and then decreasing. It kind of already tells you that right there. This is the maximum. Decreasing and increasing, that creates a minimum. Okay? So if you ever forget, you can always just draw it out. And using that kind of also lets you know that you're increasing, then you're decreasing, then you're increasing for your function. So you kind of see the cubic already forming, correct? We already know where our maximum is located, where our minimum is located. But we can use the second derivative to figure out the intervals in which is concave up and concave down. Now, will it ask you to find all these things increasing, where the extrema is, where it's concave up, where there's an inflection point? No. I mean, they could, but more than likely they probably won't. They might only ask for certain pieces. They might even ask you to show that the relative maximum is at -1/7. How do you show it? Doing the algebra, doing the number line, taking the derivative, setting it equal to 0. Do the number line, do the test points. It's all the math to show that, okay? So you have to be able to recognize which is which. It might ask you to determine where it's concave up or concave down. You take the second derivative to do that. What is the second derivative of the function? 12x minus 6, okay? You set that equal to 0 because you're going to have to figure out where is that point where you use your number line and plug in your test points. So if I set this equal to 0, I add 6, divide by 12, x is equal to 1/2. Now, 1/2 could potentially be the x-coordinate of my inflection point. I mean, it is the value where the second derivative equals 0. But in order to determine if it is indeed an inflection point, not only does the second derivative have to equal 0, or it's the value that the second derivative equals 0, but it also has to change signs on the number line. So we make, again, another number line, and we pick test points. What's a number that's less than 1/2? 0. And a number that's greater than 1/2? 1. Now you could have picked -2, you could have picked +5. Either one is still going to get you the same result. But this particular number line is not going to tell us where it's increasing and decreasing, but where it's concave up and where it's concave down. So you're going to plug both of these test points into the second derivative because we're trying to determine concavity. That is the second derivative. So in order to do that, we need to plug those numbers into the second derivative. Pretty easy because it's a linear equation. Plug in 0 and you get what? -6. So it's going to be a negative. Plug in 1 and you get +6. So it's going to be a positive. So by setting the second derivative equal to 0 and finding that x value and then doing a number line and seeing that it changes signs, we have an inflection point. That inflection point happens when x is 1/2 on the original. How do we find the y-coordinate? Plug it in. So we have a -13/2. So about 1/2 and -6.5, that's where our inflection point is. And that also means that from where to where is it concave up? From where to where? 1/2 to infinity. And where's it concave down? Okay? There you go. Concave up, and then concave down with the inflection point. Make sure that when you are graphing this, you want to make sure that it is distinguishable. You are changing from being concave down to being concave up. So we're going to take all these things and we're going to sketch the graph, okay? Using the information we found, any intercepts that we can determine, and if there are any asymptotes, then we also include those as well, okay? Intercepts. This is a cubic, right? Might not be able to, well, what was the original function? It was 2x cubed minus 12x. What is our y-intercept? What is it? It's 0, 0, right? Because y-intercept, you plug 0 in for x and you solve. what's my x-intercept? You guys told me before we have to take this and set it equal to 0. Anything in common? An x. So if I factor out an x, that leaves me with a 2x squared minus 3x minus 12. I can factor that to try to figure out what my other x-intercepts are, correct? Let's do that. So this one doesn't factor. We do know that x 0, 0 is an x-intercept, but this doesn't factor. It's going to give us a quadratic, if anything, okay? But it is a cubic, which means it is going to cross the x-axis at some point. So let's just use the fact that we know that we have a y-intercept of 0, 0. Since it doesn't factor nicely, not really going to penalize us for not having where the x-intercepts are. So we have 1, 0, 0. We have a max at negative 1, 7. So negative 1, 7. And we have a min at 2. What was the min? Negative 20. So we have a max, bless you, we have a min, and we also have an inflection point. Where's the inflection point? I know it was 1/2, negative 13 over 2, which is basically negative 6.5. So at this point right here, the graph is going to change from being concave down to concave up. Then all we do is we just connect it, okay? If you want, you can go this way. It's increasing from negative infinity to negative 1. It is decreasing afterwards. Now you can see just on this first part, the graph is concave down, correct? After 1/2, it's going to be concave up. You want to make sure that you distinguish and you change directions. I'm still decreasing, and now I'm increasing. And there's your cubic. Distinguishing that at this particular point, I am changing from being concave down to concave up. I'm increasing from negative 50 to negative 1, decreasing from negative 1 to 2, and increasing afterwards. And I did go through my intercept. And there you go. Looks just like a cubic, doesn't it? So that's how you use derivatives to graph functions. Now that you have an example, are there any questions? All right, take a look at the next one. This is an example of a what? A rational function. Rational functions have what features in them? Asymptotes. Okay? How do you find your vertical asymptote? Who remembers? So the denominator equal to 0. So if I solve this out, that's x squared equals 1. X equals, say it again, plus or minus 1. Okay? So you have x equals 1 and x equals negative 1. It is important to determine where there are any vertical asymptotes because when you make your number lines, that's for the first derivative as well as for the second derivative, those are critical numbers, okay? Those are critical numbers because that's where there's a break. That's where there's a break in our domain. That's where there's a break in our graph. So even when we set the first derivative equal to 0 and we figure out what number that is, we still have to include our asymptotes as well on that number line, okay? What about horizontal? Who remembers how to find horizontal asymptotes? Look at the degree. If they're equal like they are in this case, it's the coefficients. In this case, it's going to be, so y equals 1. When we go to graph it at the very end, we need to make sure we include both of these, okay? And while I'm at it, what's my y-intercept? is going to be, what is the point? 0, 4. Remember, you plug 0 in for x to find your y-intercept. And you did it backwards. You can actually give me my x-intercepts. It's going to be plus or minus 2. Because remember, to find your x-intercepts, you basically set that equal to 0, which is essentially setting the numerator equal to 0. Add 4, take the square root. So we have all the additional information that's going to be used at the end to graph. Now, let's do the first part. I'm going to let you guys try to do it on your own. You're trying to determine where the graph is increasing and where it's decreasing, which means you need to do the first derivative and set it equal to 0. So I'm going to let you guys do that. I'll check back in about 3 minutes. So first derivative. So we have to low d high minus high d low all over low, low, okay? You don't have to expand that bottom. Remember what I said. You don't have to expand it, okay? You simplify the top. That's 2x cubed minus 2x squared minus 2x cubed plus 8x. You guys get a plus 8x? Remember, you got to distribute that negative over. Okay? That simplifies down to be a 6x all over x squared minus 1 squared. That is your first derivative. Then you have to set that equal to 0. When you do, you'll get 0 equals 6x. So you also have a critical number of 0. A critical point is stationary point of 0. So when you do your number line, not only are you going to include 0, but you're also going to include your asymptotes because there's something happening in between your asymptotes and that stationary point, okay? So you actually have 4 regions that you have to do test points for. Did you guys get that? You get the 4 regions? Maybe you plugged in -2, maybe -1/2, +1/2, and +2. All of those you're plugging into the derivative, okay? The derivative. When you plugged in -2, did you get positive or negative? Huh? You got a negative. Because think about it, when you plug into the bottom, that becomes positive no matter what. Because you're squaring it not just once, but you're squaring it twice. Okay? And then, but when you plug into the numerator, that's what's going to actually really tell you if you're going to have a positive or a negative. When you plug in -1/2, negative. When you plug in a +1/2, and we plug in a +2. So essentially, you can have values where it's neither positive nor, like it doesn't change positive and negative. You can't have that. I think I mentioned that before. You can't have that, okay? So our function is increasing from 0 to 1, because remember there's an asymptote there, and then after 1 it's still increasing. But then it's decreasing from -1.
Teachers, please pardon the interruption at this time.
It's going to be to -1, and then it's going to continue to decrease after the asymptote until 0. Okay? Questions about that? Anything? Okay. So then the next part says that you have to determine whether there's any extrema using your first derivative test. Well, there's the number line. At -1, it keeps negative. It's still decreasing, so it doesn't change. But at 0, it goes from negative to positive. So what's happening at 0? It's a relative what? Think about it. It's decreasing and then it's increasing. That forms a what? A min. So I have a relative min that's happening at 0, comma, plug it back into the original. 4. The same spot where you found your y-intercept, yes, that is actually a minimum that's happening there. And then, of course, at 1 is still increasing and increasing, so there's only a relative min on this problem, on this function. Okay? Now, I know I gave you like a lot of space for this section, so if you want to do the next part in that extra space, I would go ahead and do that. Because now you have to do what? The second derivative. You got to figure out where's concave up and concave down. Okay? And you still have to take into account the asymptotes. Okay? When you make your number line. So now find the second derivative, make your number line, and then I'll check back in about 5 minutes.
But wait, you can't do that with the other equation.
And then I took it at 2.
You can't take out.
Yeah, she put 4. Well, you can take it out next.
This was the first derivative, right? Yeah. So second derivative does involve quotient as well as chain. You have a low D high minus high D low. D low is the chain, okay? You bring the 2 to the front with respect to the inside, being multiplied by the derivative of the inside. Did you guys get that?
Yeah.
And it's all over low squared. Okay? Now I am going to simplify this just a little bit, okay? Not too much. I'm just going to do 6x squared minus 1 squared, and then I'm going to multiply the 6x, the 2 on the outside, and the 2x together to get a minus 24x, x squared, and then x squared minus 1. Okay? And then on the bottom, I'm going to get an x squared minus 1 to the 4th power. Now, remember what I said about the whole don't expand it out, because there's a possibility that one of the factors at the top would cancel with the bottom. And here's a prime example. Every single term has an x squared minus 1 in common, don't they? So you lose the 2 here, you lose this term here, and then you lose 1 here. So that's going to turn to a 3. That one up there is a 1. So right now, you have a 6x squared minus 1 minus 24x squared all over x squared minus 1 to the 3rd power. Distribute over. And simplify, you have a negative 18x squared minus 6 all over x squared minus 1 to the 3rd power. That is your second derivative. Okay? When you set that equal to 0, basically your denominator goes away and just left with the negative 18x squared minus 6 equal to 0. Add over 6, divide by negative 18, and you get a negative 1/3. Can you take the square root of a negative number? You can, but you're not going to get a real number, are you? It's going to be imaginary.
Yeah.
Do we graph imaginary numbers on the xy axis? No, we don't. So this right here, when we take the square root, it's going to give us no inflection point. Because in order for there to be an inflection point, that means there has to be a real value that when you set the second derivative equal to 0, that you get a real value. But that still doesn't mean that we cannot do our number line, because we still have those asymptotes that we have to be aware of. Okay? So we'll do our second derivative. Click our text points and plug into our second derivative. Negative 2, 0, positive 2. We still need to figure out where it's concave up and where it's concave down. When I plug in a negative 2, okay? A negative 2 squared is a positive 4. 4 times a negative 18 is going to give me a negative something, right? And then when I subtract 6, it's still going to be negative, correct? So I have a negative number on the top. When I plug in negative 2 on the bottom, do I get a positive or a negative? When I plug in negative 2 at the bottom, is that going to be positive or negative? Positive. So a negative over a positive is a negative. Plug in 0. 0 is a little bit easier. When you plug in 0, this term goes away. The first one goes away. You're just left with a negative 6 over a negative 1 to the 3rd power. Negative 6 over a negative 1 to the 3rd power. Negative 1 to the 3rd power is what? Negative 1. Negative 6 divided by negative 1 is a positive. So we're concave up from negative 1 to positive 1. And when I plug in a 2, don't I get the same result that I would get if I plugged in a negative 2? So it's still negative. So I'm concave down from negative infinity to negative 1 and 1 to infinity. graph this. Starting with the very beginning, you know, we found our horizontal and our vertical asymptotes. We had a vertical asymptote at -1 and +1. We had a horizontal at +1. Okay, help me out with the rest. We had y-intercepts and x-intercepts, didn't we? What was my x-intercept? So we had an x-intercept at +2, -2, a y-intercept where? Now at 0, 4 was also supposed to be a relative minimum, okay? And we were decreasing from -infinity to -1. So we're decreasing, going down. And we were also concave down from -infinity to -1. This is concave down right here. We were decreasing from 1 to 0 and then increasing from 0 to 1. And we were also concave up from -1 to 1. Lastly, we were increasing from 1 to infinity, and we were concave down from 1 to infinity. So increasing, and this is still concave down, and there's the graph of your rational function. Okay? Now a lot of the rational functions we dealt with in that particular unit kind of look like this. This is also a rational function. We never really dealt with ones that had the two asymptotes with the parabola in the middle. But there you go. You can use derivatives to help you graph those rational functions, okay? Questions? This last one, I want you guys to work on till the bell rings to head us down to morning meeting. But these two that are up here on the board, those two are your homework, so make sure you guys write these down, okay? You're doing basically the same thing that we've been doing with these 3 problems. You're going to do the same thing with these 2. So the bottom 2 are for your homework, but I do want you to work on the one that's x to the 3rd right now.